All right, let's get right to it. As Chief Systems Engineer, I'm here to walk you through the master plan for something I believe is truly groundbreaking, a world-class microelectric vehicle built from the ground up from a totally blank sheet of paper. This isn't just another car design. This is the strategic blueprint for a vehicle that's going to completely redefine this entire category.
Okay, so first things first, we all need a bit of a mental reset. The whole idea of a micro EV being a glorified golf cart, a toy car, that era is officially over. It's done. What we're seeing is a perfect storm of new regulations, what customers actually want, and new tech that's forcing us to create a real, serious, and sophisticated vehicle.
And this is exactly what's kicking off that reset. We are literally heading into a revolution in how these small vehicles are engineered, and it's all being driven by this tidal wave of new global regulations. This isn't just a slow, gradual change. It's a complete reinvention of what a micro EV can and frankly must be.
And when I say a wave, I mean a tsunami, and it's set to hit in 2026. Look at what's happening. In China, they're not messing around. They're mandating insane energy efficiency and a new battery standard that basically says no fire, no explosion, period. At the same time, the EU is getting really serious about safety for its L7E class. Even the big players are scrambling to keep up. So what does this all mean? The days of lax rules are gone. Real automotive-grade engineering is now the price of admission.
So, this brings us to the most crucial point in the entire process. Before we design a single bolt, before we write a single line of code, we have to precisely define what we're building. Our mission is to engineer a single global platform that can slice through this regulatory jungle and succeed everywhere, not just in one corner of the world. Let's start with Europe. Our entry point there is the L7N class, or heavy quadricycle. Now, for years, these vehicles got a pass on real crash testing, but that's the risk right there. Recent tests show these things just disintegrate in a 50-kilometer-per-hour crash. For us, just meeting the bare minimum standard, that's not an option. It's a massive liability. We have to engineer for what happens in the real world. And this puzzle just gets more complicated when you look at the whole world. In Europe, we're capped at 15 kilowatts of power. But in China, we need to meet full passenger car safety standards. Then you've got Japan with its own unique class, and the US, where these are limited to just 25 miles per hour. So how do you solve this? You don't build 4 different cars. You engineer what we call a smart platform. One core vehicle built to the highest safety standard for China that can be tweaked for Europe and simply software limited for the US. So when we look at who's out there today, the gaps in the market become crystal clear. The Citroën Ami, the Toyota C-Pod, they're really just 2-seaters for quick city trips. The Wuling is closer, but its charging is a weak point. Our vehicle technical specifications, our VTS, are laser-focused on these gaps. We're building a true 4-seater, it's going to be highway capable, and DC fast charging isn't an option, it's standard. So this is it. This is our engineering constitution. These are our non-negotiables. 4 seats for real utility, a top speed of 100 kilometers per hour so you can actually get on the highway, zippy acceleration for city driving, real brakes with ABS, and, most importantly, a high-strength steel cage body. We're designing a vehicle that feels solid, that feels like a real car, not a flimsy compromise. And this number right here, this is our North Star. Less than 9.0 kilowatt hours per 100 kilometers. This isn't just a vague target, it is a hard requirement. We've engineered everything around hitting this number, not just to beat China's 2026 rule, but to give us a massive competitive edge in efficiency. Okay, now let's get into the guts of this machine, because there is one single decision that has a bigger impact on cost, performance, and efficiency than anything else, and that's the core electrical architecture, the system voltage. So the big question for the team was, which way do we go? Do we use a low voltage 48-volt system, a super high voltage 350-volt system like you'd find in a big EV, or is there a better way? It's all about finding that perfect, optimal balance between what it costs, how efficient it is, and the performance we've promised. And this really breaks down the trade-offs. Sure, 48 volts sounds safe. It's low voltage. The problem? To get the power we need, the electrical current would be astronomical. We're talking about incredibly thick, heavy, and expensive copper cables that just waste energy as heat. On the flip side, 350 volts is like using a sledgehammer to crack a nut. It's fantastic tech, but the components are so expensive it would completely blow up our budget. Which is what led us to this breakthrough. For our specific vehicle targets, 96 volts is without a doubt the strategic sweet spot.
It hits that perfect balance. It lets us use really efficient, industrial-grade components that don't cost a fortune. It simply gives us the absolute best performance per dollar, period. And we're pairing that 96-volt system with a battery pack that's all about safety and smart design. We're using LFP chemistry. Why? Because it's incredibly safe, it lasts forever, and it's cost-effective. We're also using a cell-to-pack design, which means we get rid of a bunch of unnecessary packaging to cram in more energy. It's just the smartest way to hit all our targets at once. Of course, having a great powertrain is useless if you don't have an equally great chassis and body to put it in. And this, right here, is where we really draw the line between our vehicle and the so-called toys of the past. Look, in this space, you've traditionally had two choices. You can build a space frame, basically a welded tube frame with plastic panels snapped on. It's cheap to get started, but it's not great in a side impact. The other option is a modern unibody, just like a regular car. Super safe, super rigid, but the investment in tooling is astronomical. Neither one was right for us.
So we engineered a third way. We call it the hybrid skeleton, and it gives us the best of both worlds. We start with a super rigid, stamped steel floor that acts like armor for the battery. Then we build a high-strength steel safety cage on top of that to protect the people inside. And finally, we wrap it all in lightweight, affordable plastic panels. It's an elegant solution that gives us big car safety with small car economics.
And this real car philosophy goes all the way down to the suspension. We're using a proper McPherson strut front suspension and a tough 3-link setup in the back. You will not find any cheap, bouncy leaf springs on this vehicle. And we made electric power steering standard because, trust me, at 100 kilometers per hour, that's not a luxury feature, it's a core safety system.
Okay, so we've got the strategy, we've got the core engineering defined. So let's zoom out and look at the roadmap. How do we take this blueprint from a presentation to an actual assembly line?
We are running this on an aggressive 24-month plan. The clock is ticking. In 4 months, the design is locked. By month 12, we'll be testing physical prototypes. And at the 24-month mark, the first cars will be rolling off the production line for customers. Is it a tough schedule? You bet. But we've benchmarked it against the best in the business, and we know it's achievable.
Now, hitting these goals also means being smart about what we don't build. And this is a perfect example. We're getting rid of the built-in infotainment screen. Why? It's expensive, and it's outdated in 3 years. Instead, we're building a great app that seamlessly integrates with your smartphone. This one move saves us over $200 a car and gives the driver an interface that's always up to date.
When it's all said and done, every single spec, every material we've chosen, every engineering decision we've talked about today, it all comes back to this one core philosophy. The next generation of these cars can't just be appliances. They absolutely must have the soul of a car. That means they're safe, they're efficient, they're useful, and they're actually enjoyable to drive.
Which leaves us all with one final question to think about. What really happens when the smallest cars on the road are finally designed and engineered with the same passion and the same rigor that we put into the largest, most expensive ones? Well, that is the vehicle we are building, and we truly believe that it's more than just a new product. It's a fundamental shift in the future of how we move.